G'day, in this video we're going to be looking at applying our understanding of waves and standing waves to the concept of harmonics, quite an important concept in the world of music. Particularly our focus will be on harmonics in a string. Now, syllabus dot point 3.3.6 does focus on fundamental and harmonic frequencies and asks us to look at the behavior of standing waves on strings or possibly in pipes. We can do both. This video is going to focus primarily on strings. The last couple of slides will look at pipes really briefly, but the major focus of what we're going to be covering in class is strings. So our focus today is going to be to relate standing waves in a string to fundamental vibrations and harmonics, then look at the quantitative relationships between these harmonics and their resulting frequencies and wavelengths, and then look at factors which can influence standing waves in a string. They're namely going to be tension and mass. So for a standing wave to form, you need to have a wave interacting with itself. The wave is being produced at one end continuously and then is being reflected back onto itself. And when you have those superposed waves interacting with each other, that's leading to essentially this standing wave, a wave that is being made, but it doesn't actually look like it's propagating anymore. You have these areas which are your nodes, areas where there's permanent destructive interference, which keeps that part of the wave still. And then you have these antinodes, areas of maximum displacement associated with the amplitude of the wave. Standing waves can take many forms or modes. The most basic one is the one that you can see here. This is the fundamental mode of vibration, or the first harmonic. Essentially, it has two nodes, one on either end, and then the antinode, the single antinode in the middle. Essentially, this represents half a wave. However, as we begin to add in more sets of nodes and antinodes, we start to have further harmonics. The first one here is the second harmonic. This one includes two antinodes. Following that, we have the third harmonic. This one has three antinodes. The second harmonic has added an additional half of a wave. That means that there is now one wave total from start to finish. And the third harmonic then adds, again, another half wave. We can start to see a bit of a pattern here, which means that there is one wave as well as another half wave. So 1.5 waves in total from beginning to end. As we increase our harmonics, we also increase our frequency. So for the second harmonic compared to the first, there are double the number of waves which are passing a point every second. That means essentially that the frequency is going to be double the original first harmonic. When we then look at the third harmonic, that frequency is going to be 3 times the fundamental, or the first harmonic. And that's essentially because there are 3 times as many half waves present, meaning that 3 times as many waves are going to pass a point every second. As we talked about in the last video, there is a direct relationship between frequency and pitch. The higher the frequency, the higher the pitch. So as we go from first, second to third, fourth, etc. harmonics, we are expecting to increase our pitch because we are increasing our frequency. And this is where the concept of overtones come in. Overtones imply that there has been an increase in frequency or an increase in pitch. So the first overtone is the first increase in pitch over the first harmonic, and the second overtone here is the second increase in pitch over the first harmonic. Thus, I have those terms sitting there in brackets. These harmonics that you are looking at are quite important in musical theory, and the patterns that you get in these harmonics actually drive concepts around pitch and note that you see played by musical instruments. So as I've already alluded to, there are some pretty distinct patterns between the frequency and wavelengths of each of the harmonics when they exist on a string. For wavelength, there is a relationship between the length of the string that's producing the wave and this value n here, the nth harmonic. So in this scenario, because in each of the harmonics the string length is the same, essentially when you increase the harmonic, 1, 2, 3, etc., the wavelength needs to decrease as a result. Furthermore, for frequency, as we discussed about in the slide previous, the frequency of each harmonic is going to essentially be the frequency of the fundamental multiplied by the number harmonic that we are looking at. Now, you will not find these formula in your data sheet. If you are required to use them in exam style conditions, you can probably expect to be supplied with these. I'd be much more concerned with you being able to apply these equations rather than to memorize them. Now, the final thing to look at in today's video is how the string itself can have an influence on the formation of a standing wave in a string. And that is dictated by two key variables, the tension on the string and the mass per unit length of the string as well. Both of these variables will ultimately have an influence on the velocity of the wave as it moves down the string. So for example, if you were to increase the tension on the string, you would expect that the velocity of the wave increases. And conversely, if you were to increase the mass of the string per unit length, let's say that we're going from a plastic string to a metal string, you can expect that that will decrease the velocity of the wave as it moves along the string. These two factors can have an impact on the resulting frequency of the first harmonic, and as a result have an influence on the standing wave which is being formed when that string is either being struck or plucked, say on a musical instrument. By substituting this expression in for V and doing a little bit of working out as we move along, we can find that the fundamental frequency or the first harmonic frequency is very much going to be dependent on variables like tension, mass, and the length of the string as well. Similarly to the equations previous, you will also not find this equation in your data sheet. Again, I'd be much more concerned with you applying this concept to a scenario where the equation is given rather than requiring you to memorize this equation and apply it. The way in which we analyze the frequency and wavelengths of harmonics in pipes are similar to strings, but there are some key differences. These similarities and differences do go beyond the scope of this video, but I have included some data to get you started if you do want to look at these concepts in your own time. Thank you very much. In the next video, there are two more big concepts that we're going to be covering with sound and sound waves. They are beat and the Doppler effect. So I'll see you in the next video.